Thank you. Yeah, it seems to work. I have a small introduction first to lattice structures in general and to applications, and then to our mechanical studies, and finally we will give you some idea of the applications we have been working on. Additive manufacturing has given us a new possibility to produce so-called metamaterials, so we can make functional materials, but also to control the elasticity. So for us, the original motivation was medical applications and implants, where we had a problem with the stress shielding effect, so that metals are much more stiffer than the bone tissue. So with these lattice structures, with low density structures, we were able to decrease the stiffness, so to have the same elasticity in the structures than the bone has in human body, to make better implants. But we have also been thinking of other structures, also like spring-like structures. There are some good examples from sports, for example, with polymers. And when we come to weight reduction, these lattice structures, they offer us methods to decrease the weight and to optimize the stress distribution, so that we are not working with this hotspot analysis like with solid materials. Also, we can make completely new kind of products, for example, for heat exchangers. There are some good examples from space industry now with the rocket nozzles, but they are not really utilizing any lattice structures. It's mostly like sophisticated channels that they are now doing. For this study, we have selected Gyroid and Stochastic lattices, and before the study, we have done some optimization. So this is like the preliminary study. It is already done quite far. We have already finished the clinical testing with the animals, for example, in medical applications for the same structures. The title of this presentation is the Anisotropy. So basically in the literature, we mostly can find the compressive properties for this lattice structure. It's quite easy to study. You can make very small specimens, but to measure the tensile properties, we needed to develop something new. So we came up with this kind of specimen design. So we have a gradiental change in density along the cross section, so that we have the same gauge length, both in compression testing and in tensile testing. And for manufacturability, we wanted to minimize the volume of the sample so that it is less expensive for us to print. We are running out of money as normally. So we have this kind of closed shape specimen for gripping. When we think about the tension, compression, anisotropy, I collected the yield strength and the elastic modulus here. And when we have different structures, we see completely different behavior in yield strength. With the gyroid structures, with the lowest densities, we almost had isotropic structures in between compressive and tension properties. But with gyroid structures, the trend changed completely when increasing the density. So the anisotropic grew as the density grew. But with stochastic structures, we basically saw the same trend despite of the density that was used for the specimens. In elastic modulus, we see exactly similar trend between both of these lattice structures. So the anisotropy goes higher here when the density increases. This is almost like an imaginary slide, just to think about the possibilities when we consider low density materials. So what we are comparing in our studies and what is used sometimes in literature is this super magnesium alloy with density of roughly 1.9. So we wanted to see if we can make similar meta material using these lattice structures with the same density. So we produced structures with a relative density with titanium from 10% to 50%. And the one with 40%, it basically has exactly the same density than this magnesium superalloy here that has a tension yield strength of over 200 megapascals. So what we did here is that we reached 335 megapascals with this titanium with the same density. So basically, additive manufacturing has given us a possibility to do much stronger low density materials than are possible by alloying. We have compared these results with other groups in the world, and based, like, depending on the lattice structure that we use, we have quite nice possibilities here also to control the elasticity. So here I have compared some of the results from Australian group that were aiming to make as stiff lattices as possible, in contrary to our objectives, where we tried to decrease the elasticity to meet the elasticity of the bone. So just to show that these lattice structures, they give us a possibility not only to control the strength, the density, but also the elasticity. One of the questions for us for future is that if we now basically reach the same strength, nominal effective yield strength with the lattice structures than we saw with these solid specimens, is it possible to make such smart lattices that we can actually increase the strength in respect to the density? We are not there, but I'm trying to ask if it's possible. There are a lot of different type of lattice structures available. What we have been comparing now is yield strength and elasticity and the possibilities that, with the idea that we basically won't need a single lattice structure. If we want to make like a smart product, we can combine different lattices to reach the behavior that we really want. What is the outcome of this optimization? What we have done, we have basically reached better properties, much better properties than observed in literature in general. And this is only because of the control of the material quality, the porosity and the microstructure in the printing process. So my group has been focusing on fatigue and on material quality. We have done more than 10,000 specimens, tested more than 10,000 specimens for additive manufactured metals just to create the data bank. So we have a map how the different processing parameters affect to the material quality. And based on this data, we have tried to optimize these prints so that we can have the most nicest feature, the smallest feature size in respect to the best material quality that is available with this technique. So we are really happy with these results. And what we are also happy is that we now have the tension properties determined. So what we get from the literature, it's only basically the compressive or shear stress properties that we have. And now based on this study, we see that there is a distinct difference in stiffness, in compression, and in elasticity. And if you think about implants, for example, if you broke your bone here and you put an implant, it is basically under compression. I don't know how you can put your leg on tension, but what we need is low elasticity for the implant, but high strength to keep it alive. If you are an active person, you don't want to break your implant after a year or so. This is the final slide. So we are quite far. We did this with Costa Rican University we started it like 5 years ago. Started to develop first these lattices so that we minimize the stress shielding effect. We basically have now developed lattices that are exactly meeting the properties of our bones. We made Petri dish studies to study the cell growth behavior, and after that, we optimized those lattices so that the tissues can grow much more effectively than they grow in natural structures. So we have better one produced now that you can find anywhere. We put those samples into horses. I'm sorry, the horses are not alive anymore, but the result showed that we were absolutely correct. It's not, we made an open structure with an idea. We don't need an implant to put any screws. We want the bones to grow through the implant so that the implant will finally be a part of your own body. So we tried that. So we hoped that the bone will attach to this open surface, and the best wish was that it would go through. And based on the specimens we took out from these happy horses, they were green inside the whole implant. So it was not low density material anymore. It was completely filled with bone tissue. So we come with the biocompatibility, and with additive manufacturing, we have kind of a rough surface already in the beginning. We don't need any, shot peening or cementite treatments for that. We kind of have a perfect surface already, but with these lattice structures, we can allow the bones and the other tissues to grow. And we hope that in future we don't have titanium here. We take something like magnesium that will be dissolved by the body. So then it will be more or less an optimization that if the body will grow into the implant and the implant has some fatigue strength and some reliability, so they should go in like hand by hand so that the implant wouldn't break before the bone has gone through. But we are not there yet. This is the idea for the future. And also taking into account the healthcare services, I find additive manufacturing quite perfect. If you now think about the existing implants, you have like different sizes available. You have a warehouse, you select something from these sizes. So normally you run out of something that is very, the size that is the most used one, it's out from the warehouse. But the idea here is that you have the CT scanner of the hospital, you have 3D printer. So patient, when he breaks the legs, he will be CT scanned, and then there will be our software calculating this implant, and the next machine will then print it, and the surgeon will insert to your body. So some benefits hopefully also there. Thank you.